Yeah, welcome back to relation and function part 1. In the previous lectures, we have studied set theory. Today, we will study relation and function. So before starting relation and function, let's see what is ordered pairs. For any two, for any two objects A and B, the ordered pair A comma B is notation specifying the two objects A and B in that order. Means order is very important here. If you are claiming that two ordered pairs are equal, then A must be equal to P here and B must be equal to Q here. Then only you can claim the equality of ordered pairs. Equality of ordered pairs. So when we can claim, if and only if the corresponding first elements elements are equal and the second elements are also equal. If you have two ordered pair, for example 1 comma 2 and 2 comma 1, these are not equal ordered pairs. You can see by geometry also 1 comma 2 is located here and 2 comma 1 is located here. So these two positions are not same. So these two values will not be same here. Let's see one example related to ordered pair. If I am following NCERT class 11th, so I will give you notes also after the completion of relation and function like we have given in set theory. If x plus 2 y minus 1 equal to 3 comma 1, find x and y. So I told you the equality of two ordered pairs, you have to equate the first element and second elements. So you will get x plus 2 equal to 3 and y minus 1 equal to 1. So x will be 1 here and y will be 2 here. So the value of x and y will be 1 comma 2. Ordered pair is very important in understanding of Cartesian product. Let's see Cartesian product. It is product of sets. Given two non-empty sets. First case I am considering non-empty sets. See the language here carefully. P and Q, the Cartesian product P cross Q, this is the notation, P product Q is the set of all ordered pairs of elements from P and Q such that P cross Q is given as all the ordered pair P comma Q, where P is belonging to set capital P and small q is belonging to set Q. For example, if P is a set 1 comma 5 and Q is the set 2, 3, 4, then what will be your P cross Q? Will be all the ordered pair from P to Q. So if we pick 1 from P, we have to take ordered pair with all the elements of Q here. It will be 1 comma 2, 1 comma 3, 1 comma 4. Similarly, we will take 5 from P, 5 comma 2, 5 comma 3, 5 comma 4. Similarly, we define Q cross P. We have to take elements of Q as a first element and elements of P as a second element. So it will be 2 comma 1, 2 comma 5. Similarly, 3 comma 1, 3 comma 5, 4 comma 1, 4 comma 5. We can see that 1 comma 2 is not equal to 2 comma 1. I told you previously, it means in general P cross Q is not going to be Q cross P. It means Cartesian product is not commutative for two distinct sets. If P and Q are distinct sets, I am taking here distinct sets, then commutative property is not satisfied here. If P and Q are same set, then suppose we are taking P cross P, then it will be obviously equal to P cross P. You can take first or second, it does not matter here. So let's see some remarks. First remark. If either, suppose one of the set is empty, if either P or Q is the null set or empty set, is the null set, then P cross Q will also be empty or null set. Empty set. Meaning, what is the meaning? There will be no element in the P cross Q, that will be only 5. Second remark is, two ordered pairs. I told you this, I think. In general, I told you, in general, Cartesian product is not commutative. So I have already discussed this point. Second remark is, if the cardinality of set P is small p, means there are small p elements in set capital P and there are small q element in the set capital Q, then the number of elements in P cross Q will be P into Q. Or you can say that the cardinality of P cross Q will be the PQ. What is the cardinality? I told you in the set theory, the number of elements. You can observe from here also, the cardinality of set P is here 2. You can see that number of elements in set P is 2. Number of the elements in set Q is 3. So what will be the number of elements in the P cross Q? It's the just product 2 into 3. So it will be 6. You can see here 1, 2, 3, 4, 5, 6. And one important point, the cardinality of both the set P cross Q and P cross Q and Q cross P both will be same. But in general, P cross Q is not going to be equal to the Q cross P. In general means when the sets are distinct. Okay, let's see one more remark here. Third remark is, if we take any A cross A cross A, if we multiply any set 3 times, so this will be the collection of all triplet here. Here A, B, C are the distinct elements of set A. Distinct elements, remember. Here A, B, C is called an ordered triplet. No, ABC can be any value here, not necessary distinct, not necessary. For example, suppose you have A is 1 comma 2. Then if you multiply A cross A cross A, you can see that many elements are repeated here. So not necessary distinct here. Let's see one more example. Example 2. If set P is given as ABC, set Q is given as set only element are find P cross Q and Q cross P. Also, are these two products equal? All these are these two products equal? Let's check. P cross Q is going to be A comma R, B comma R, C comma R. You can see that the cardinality of set P is 3 and cardinality of set Q is 1. So in the product there will be 3 into 1, 3 elements. If you find Q cross P, it will be R comma A, R comma B, R comma C. So this is not necessary equal because the location of A and RA can be differ here. Let's see one example as exercise for all of you. Example, let set A is 1, 2, 3, set B is 3, 4, set C is 4, 5, 6. Find part A is A cross B intersection C. D part is A cross B intersection A cross C. C part A cross B union C. D part A cross B union A cross C. And one more example I am going to discuss here. If capital P is 1 comma 2, find triplet P cross P. Let's see what is the relation. A relation R. I am representing relation by notation R. R is a relation, not real number here. Don't be confused. From a non-empty is important word here. Set A to a non-empty, also non-empty, set B is a subset of the Cartesian product of A cross B. Means R, relation R is a subset of A cross B. And how R is defined? From set A to set B. R is actually a mapping. R is a relation. I'm not using mapping word here. It is from set A to set B and it is subset of A cross B. Okay, let's introduce one more definition. Then we will see some examples. The set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of relation R. This is the definition of domain. Collection of first elements of any ordered pair. Let's see one more definition. The set of all second elements in a relation R from a set A to a set B is called the range of the relation R, range of the relation R. If R is the relation of A to B, important point, B is actually always called codomain of relation R, of relation R. A range is always subset of codomain. It can be equal to also codomain, but always subset. If equal, then it will be equal subset. So these are some important definitions. Let's see one example and try to understand what is a relation, how to define domain, range, and codomain. One important remark I am going to write here. How can be relation represented? Relation may be represented by roster form, I told you in lecture 1, or set builder form. Set builder form. So you can represent by any of the notation here. Okay. One more term I am going to use here. How to define relation properly. Another notation for relation is, if any ordered pair is in relation R, this is relation R. If any ordered pair is in relation R, we say A is related to B, and we denote it as A related to B. This is the notation. Further, I am going to follow. Please remember this. Let's see one example. Let's set A is given as 1, 2, 3, 4, 5, 6. Relation R is defined from set A to A itself. A to A itself. By R equal to, it is a collection of all ordered pairs which are satisfying the relation between, what is the relation between y and n? Y is x plus 1, y is equal to, so this is the relation between y and x, y is equal to the x plus 1 here. So what is the question now? First part is depiset this relation using arrow diagram, and B part is write down domain, codomain, and range of relation R. Let's see solution. Firstly, I am going to draw an arrow diagram. This is your set A actually here. R is a relation from A to A. See carefully, A to A. Set itself, it is defining relation from set to set itself only. This is your R relation. The elements are 1, 2, 3, 4, 5, 6. It is not defining A to B, it is taking B is equal to A only. So this element will be X here, and Y is also belonging to set here. We take a X element from here, Y element from here. And because if you see, the ordered pair now will look like A cross A. Cartesian product will be A cross A because set B is also equal to A here. So what will be the Y? When you put X equal to 1, Y will be 2. When you put X equal to 2, Y will be 3. When you put X equal to 3, Y will be 4. When you put X equal to 4, Y will be 5. When you put X equal to 5, Y will be 6. And I'm taking 1 to 6, I'm writing here. You can see that 6 is not mapped here, because 6, if you put X equal to 6, Y is going to be 7, but 7 is not belonging to set A. Similarly, here 1 is not coming from anywhere, because y will be 1 when x equal to 0. Y will be 1 when x equal to 0, but 0 is not in set A. It means there are 5 elements from this side is mapped with 5 elements of this side. So this is the arrow diagram. Now let's see what is the domain. Domain of A or relation R is equal to the collection of all first points. If you make the relation, firstly I am going to make the relation. What will be the relation here? 1 is mapping with 2, 1 comma 2, 2 is mapping with 3, 3 is mapping with 4, 4 is mapping with 5, and 5 is mapping with 6. This is only because 6 is not mapping with anyone. So what will be the domain of R? Domain of R, I am not in first element, collection of first elements. So it will be 1, 2, 3, 4, 5. I told you this definition earlier. Collection of first elements. You can see that collection of all first elements of the ordered pairs. Now, what will be the range here? Collection of second elements. So what is the second element? 2, 3, 4, 5, 6. This is the range. What about codomain? Codomain is interesting here. I am writing here. Codomain. Codomain is always this set. Codomain is always this set. So it will be equal to A only, or 1, 2, 3, 4, 5, 6. So here you can see that range is subset of codomain. Here range is subset of codomain because all the elements of range is belonging to codomain. So this is the first example. Let's see one important remark here. The total number, it is most important remark actually. The total number of relations that can be defined from a set A to a set B to a set B is the number of possible subsets of A cross B. A cross B. Possible subsets of A cross B means if number of elements in set A is P, number of elements in set B is Q, the number of elements in A cross B is going to be PQ, then number of relations from A to B will be 2 to the power PQ. Let's see some easy proof here. Easy proof. You have a new set A cross B. Call it as A cross B, call it as EZ. So in the number of elements in set E is now PQ. So if we make the number of subsets of set E, I told you the number of subset of any set is 2 to the power cardinality of the set. This is the definition of number of subsets. 2 to the power cardinality of any set. Here set is E here, or E is equal to A cross B. And I told you this proof using the binomial expansion in the lecture 2. So it will be equal to 2 to the power, what is the cardinality of set E here? That is PQ. So number of subset of A cross B is going to be power 2 to the power PQ. And all the subsets become a relation always. Phi is also relation. Phi is also relation that is called empty relation. I'm going to discuss that one. So this is the way, this is the formula to find the number of relations from all the total number of relations from set A to set B. Let's see some more remarks here. First remark here. A relation R from set A to set A means A to A is also called or stated as a relation on A. We call relation on A. It means it is A to A only. A to A only. One definition I am going to add here. A relation R in a set A, it means I am taking A to A here. I am taking A to A here. Means domain and codomain both are set A. It's called empty relation. Empty relation. If no element of A is related to any element of A, because we are taking A to A na, it means no element of this is related to set this, such that R is null set, that is always subset of A cross A. So this is called null set. One more definition I am going to add here, that is called universal set. A relation R in a set A means domain and codomain both are A here. It's called universal set, universal relation if each element of A is related to, means I am collecting all, each element related to every element of A, means I am taking completely Cartesian product of A cross A. Then this relation is called universal relation. And these both are phi and A cross A are called here trivial relation. New name for both these, trivial relation. In the next lecture, we will see the type of relations, and we will study reflexive, symmetric, transitive and antisymmetric relation, and we also study what is the equivalence relation. Okay, thank you.